Thank you. Um, Today we will talk about the electronic and magnetic excitation in two-dimensional material. This to work under Professor Mike Cottom supervision. Our roadmap today, or table of contents, we will take first about two-dimensional material, electronic and magnetic properties, the importance of this material, and the theoretical method employed to study these properties. Actually, the properties have two main factors, so we'll study first the effect of the ring of interaction and the two-dimensional lattice structure of the electronic and magnetic properties of two-dimensional material. In range interaction, we have two range, nearest neighbor range and next nearest neighbor range. In first of our research, we fixing only we have nearest neighbor. We have only nearest neighbor, and then after we finish our tool, we will apply next nearest neighbor. In the two-dimensional lattice structure, we study square lattice and honeycomb lattice. In honeycomb lattice, we have two type of stripe. We have zigzag and armchair, depend on the edge shape. We have armchair edge and we have zigzag edge. And in zigzag edge, we have spatial zigzag edge states, localized edge state. So in our first presenting, we have the result of next neighbor with square lattice, next neighbor with honeycomb, zigzag and armchair, and with nearest neighbor we have studied the zigzag edge, and then after that we will add nearest neighbor and what impurities to see how to tunable the properties, electronic and magnetic properties of two-dimensional material. And the final thing, we will make two-dimensional bilayer system to understand how to have very good tools to tune the electronic and the magnetic properties of two-dimensional for the application. We know that the technology is very linked to our knowledge of physics, especially in material science. We have what we call Kurzweil extension of Morse law. He found that technology actually is extension for our knowledge and our research for material. In the computation field, for example, we have here electromechanical. When the technology not able to follow the extension, we found Rayleigh and then vacuum tube, then transistor, and then integrated circuit. The integrated circuit, which Morse law period now, actually depend on three-dimensional semiconductor. The three-dimensional semiconductor actually begin to face soon technical and scientific problem, since we can't miniaturization anymore number of transistor in due to the heat effect. So the industry began to explore the number of alternative devices technology. And in this paper in Nature, they said they begin the research focus to looking in electron restricted in low dimensional material like zero dimension like quantum dot, and one dimension like nanotube, and the two dimension which famous now famous material now, which our subject today is two dimensional material. The spark of this research is coming from graphene properties. We know in 2004, Game and Nufuzalov with very simple technique used Scotch tab, able to isolate one flag of carbon with thickness one layer with graphene, and when they measure the properties, they found superior properties, the most stuff one, the most fast one, electrons. That is very, very. It began actually what we call now gold rush for graphene application. They try to make a lot of application using graphene, and they expecting that graphene will replace silicon in few years, in our next 15 years at least, will be able to replace silicon by graphene. In 2010, actually, they take Nobel Prize for this ground-breaking experiment regarding the two-dimensional material graphene. At the same time, we have advanced in magnetic fabrication technique. Now, the scientist using nanofabrication technique was able to make a hexagonal lattice of 10 nanometer magnetic nanodot, and in this case we have two-dimensional nanomagnetic ferromagnetic dot, and they study their properties and study, for example, here fabricate ferromagnetic honeycomb nanoscale network. Actually, this means that most of people now in hot research in graphene and in magnetic material try to focus to make the two-dimensional material replacing silicon and get new properties that allow to us to extend Moore's law and have a lot of applications. To study the two-dimensional material electronic and magnetic properties, as we know from physics, we have to solve the Schrödinger equation for the two-dimensional material. But two-dimensional Schrödinger equation have only few systems we have exact solution, and most of the time we use approximation to solve the Schrödinger equation. In this research, we're using for electronic properties tight binding approximation, in which the electron and the magnus, in the case of the same approximation, is spent most of the time occupying their own lattice side and really jump from one side to another side in the two-dimensional lattice. Tight binding approximation expressed in second quantization language can be represented by operators, and we have a particle leaving a side is the particle annihilation event, which is represented by annihilation operator. In case we have a particle moving to a new side, is a particle creation event, which is represented by a creation operator. When we write the Hamiltonian of graphene, we have here the structure of graphene. In honeycomb lattice, we don't have a previous lattice, which means we can't have a single lattice that can, with translation vector, we can find the periodicity. So we have two sublattices, triangular sublattice A and B, and in this case, we can formulate the move of electron in these two sublattices using this Hamiltonian. In first case, we're using next neighbor. It means that the electron jump only in the nearest neighbor for him. And then we add the next nearest neighbor, which means that the electron will jump for more far, next far electron here, side here. And we will have the Hamiltonian in that form. It means creating electron inside A, destroy, annihilate electron inside B, and the energy for hopping is this one. And in next neighbor, it will be T1 here, the same energy for moving from next to nearest neighbor. For magnetic excitation, we use Heisenberg Hamiltonian when exchange between the spin sides is affected by the spin rotation of every side, and this term is the Heisenberg energy. And we have applying electric magnetic field in the direction of Z. We have here the projection of Z. This is the potential energy for Zeeman effect, and we add the anisotropy term in this direction, which uses this direction. It will be in this term, because any disturbance in the system in very low temperature will create excitation, as this excitation is no more than spin wave here, and spin wave actually can be excited by any given energy for low temperature, like high electromagnetic wave. To treat that in second the quantization language, we use Halstein-Primakov transformation. We can express this Hamiltonian in this second form, second quantization language. After we have the Schrödinger equation, or write the Hamiltonian, we can use the equation of motion to study the time evolution of the properties of the material. We have two methods. One method that we can try both all the material properties in diagonal, and off diagonal here is all zero except this only up and down is -1. This is called tri-diagonal method. Or we can use exchange sum or hopping sum, study the movement of electron for next neighbor here, for example, and we have formulate the equation in eigenvalue matrix equation. For solving this one will give us the dispersion relation. One advantage of tri-diagonal method is we able to distinguish between edge mode and area mode, and we know in the small nanomaterial, edge contribution for the properties is very important. This method is very simple. We can separate the edge properties by creating two matrices. Here, one contain all bulk material, and one contain only the edge properties. In this case, here, we can, by some physical condition, we can find the edge mode. It's supposed to be real and less than 1. And for area modes, we have to imagine it, and the modulus is less than 1. We studied tri-diagonal method, use it especially in our research to study the square lattice, and we study zigzag edge localized. Actually, due to we have a lot of results, we here only present some of our results due to the huge number of results. The first result we will show is the two-dimensional square lattice. We have a square lattice here. The alignment of spin in the direction, and we have only nearest neighbor interaction. It's very interesting from basic science because it's important for example, high temperature superconductor to understand the physics of two-dimensional square lattice for anti-ferromagnetic. For us, it's very important to study this system for magnetic application like magnetic memory, switches, and the magnetic resistance. The result of our calculations show here we have here the frequency, and we have here the wave vector in the first Brillouin zone, and this is the boundary of our bulk, our area mode, and then we have the edge mode. We see here that very important, excited for us, that we have only optical mode for edge and for area mode. As we increase the number of row, we have increasing the number here of the edge mode, and as we see, we increase the number of row, we move to quasi-continuous band, and as we see here, the edge mode is collapse. One of the very important results for is the basic physics behind that we have unexpected features that area and edge spin wave only exist in optical modes. It means that we don't have acoustic modes, which usually we found in systems like that. This maybe enable us to find out more interesting physics for two-dimensional square lattice. After that, we begin to study two-dimensional honeycomb lattice. We saw that the superior physical properties of graphene coming from its crystal structure as two-dimensional honeycomb lattice and its short range interaction. The question arises to us, can we make a ferromagnetic counterpart for graphene? Also, we don't have elements that can form two-dimensional honeycomb ferromagnetic lattice, but we can use artificial nanodots to form this one. And in this case, we will have both crystal structure and range interaction, and we expecting that the behavior, the properties will be very similar to graphene, which means we can lead to new technology, especially in spintronic devices when spin properties of electron is used. So we begin to study this system. We have here nanodot of ferromagnetic arrayed in zigzag stripe or armchair stripe. We can actually put some impurity with different magnetic material here in these lines. The result, we use the result of E-matrix method for this study, and here for zigzag stripe case, we found that we have for even stripes, we have this dispersion relation here, the wave vector in first Brillouin zone, here the frequency. The same here for the odd. We found that we have odd and even the even contains very similar result obtained in graphene counterpart. So we found that our result here is very coincidence with graphene material. Also, this is a magnetic properties. When we add line of impurity, actually we separate the ribbon to be sub uh, two sub stripes interact together, and we have extended localized state. Here's the same as we see here. When we put the second line, we have here extended line, which show that we have like accumulation size for Magnum. We see that our case for zigzag stripe, we don't have gap. So the most important property is actually the edge localized state near Fermi level. So we use to study relative density of state near Fermi level and see how the changing the edge properties can affect this the quantity. Can we also the width of the ribbon, how it affects the number or the relative density of state for Fermi level. We also study to understand any physical parameters that can change the properties of zigzag ribbon. We use the relative density of state of center band here. So we can measure the number of points here, which will reflect any effect for edge, for example, for the width, for impurities. Here, the effect of size strip width on the relative density of state near Fermi level. For even number, we have this one. For odd number, we have this straight line. Actually, for even number, is compatible with another research published for graphene. For the stripe, we have the same geometry. With even number, we have increasing in the number of relative density of state as we increasing the width of the stripe. Here, we measure the effect of stripe width on the density, relative density of state of center band. As we see here, it increases. We don't have, like here, the body is not affected very much, odd and even nearly the same. This comes because the center band measure all, even the Fermi level states within this parameter. We didn't show all the results because we don't have enough time for that. After that, we have studied the armchair stripes, and we found that, as the case of graphene exactly, that we have three types of stripe. We have 3i, 3i plus 1, 3i plus 2, where i is number 0, 1, 2, and this describes the number of row. So we have three kinds of stripes in the armature stripe here for magnetic properties. The first one here is 20, belonging to 3i plus 2. We don't have a gap here, but we have point contact at drag point here. But for case 3i plus 1, we have here a gap. We introduce some. This result is exactly coincidence with with electronic graphene stripes, which shows that we have coincidence between electronic graphene and magnetic stripe with nanodot when we solve the dispersion relation. Adding one line, actually, as we see here, it's as we said in the exact case, we have two substripes interact together, and these two substripes is interacted together. We have here reducing. We reduce our. We have degeneracy, increase the degeneracy. We see here, and we have the line that coming from the impurity with extended localized state at Fermi level. But the second line, we have here changed the dispersion relation, which shows that we, by both many lines of impurities, we can tune the dispersion relation for magnetic stripes. In these stripes, we have, it's very important to study the energy gap. Energy gap actually is one of the main properties of the armature stripes. Here we find that we have for 3i and 3i plus 1, we have this dependence which is proportional to reverse of the width here. While for 3i plus 1, we don't have energy gap. This is exactly a relation found for graphene counterpart, which shows that we have nearly the same dispersion relation for magnetic nanostripe. To study the variation of energy gap against the strength of exchange for armature stripe, we here the energy gap, we here the edge properties to the bulk, and we see here the change of the energy band gap. As we see here, for 20, which is 3i plus 2, we have no energy gap until it's 1, and then we can open the gap. For 21, which is 3i, we have here small, and then at half it's closed, and then it's open again, and then go slowly decreasing. For 22, we have the very different one, from 0 at maximum here, and then at 2 go to 0, then increases. We study also the variation of energy gap against the strength of the impurity exchange with the impurity line. We put the impurity line as the 11th line of the armature strap for the 3 strap types, and study the change of energy gap with the change of the impurity with respect to the bulk, the area exchange. As we see, the same behavior as we see before, but with different maximum and minimum here. Actually, this enables us to, when we fabricate a magnetic nanomaterial, we can, for engineering purpose, we can choose which gap, when we choose the gap, energy gap requires the energy gap, we can choose from these figures, table. To also, to make it very useful, we make contour, we make color contour plot of the energy gap for the armature stripe width, 20, 21, and 22 left side here. Here is the position of the impurity line. Here is the impurity exchange parameter, and we change both the position and the exchange of the impurity. And here the color is from black is small to red is high for energy gap. As we see here, we have symmetry allowed the half of the ribbon. The same for the also 3 stripe, and it's very helpful to know which way we can choose the highest energy band gap. We added the second line to see the effect. We fix the first line at 11, and it changes the second line impurity line position and impurity exchange GI. And as we see here, we broke the symmetry for 20 and 22, but for 21 is not broke symmetry for the energy band gap with the change of the position and the impurity exchange. The result of this honeycomb lattice dimension for ferromagnetic show the coincidence with the result of graphene nano-ribbon result by electronic tied binding Hamiltonian. From technological point of view, these results are very encouraging to fabricate a magnetic counterpart to graphene, which will lead to a new technology, especially in the field of spintronic devices and magnetic application. One of the main results that the result shows that many obtained research results of graphene can be easily applicable to magnetic counterpart case. In case of zigzag stripe graphene nano ribbon, we have very famous here bipolar flat localized edge state at Fermi levels here. Actually, a lot of experimental, this come from calculation, but experiment, we don't, a lot of experimental results fabricated of graphene nano ribbon found that is not here semi-metallic, but found experimented semiconductor behavior, which is consequence that this is, actually is not exist at Fermi level. To solve this ecosystem between the theoretical models and the experiment, we using another method for solving to study this edge localized state. In previous calculations, they using boundary condition that cancels the edge effect. So in this way, we try to use tri-diagonal method, which with similarity of crystal structure of Heisenberg and ferromagnetic, and the structure of the graphene nano ribbon for semi-infinite one, we found this structure can let us to follow the tri-diagonal method step used to study before Heisenberg and ferromagnetic, which is using tri-diagonal method. For summarizing the result we show here, edge localized state for edge with different edge hopping here. With tridiagonal method, the shaded area is the mode continuum, and we have here the frequency, here the wave vector, and as we see in this case, we have interaction between the edge and the area lines. We found that in most cases here, in zero edge hopping, it will have extended one. As we increase hopping, it's decrease, but it's come moving here and here. And especially in half, we have very similar one that found in theoretical calculation, but they always found this like 0.05. They found it here in Fermi level, but here due to the effect of edge, different hopping parameter, which shifted to up. To summarize this result, we study in this figure. We calculate the total relative localized density of state, which is black point here, and the relative localized density of state near Fermi level, which is red one, and the left of percentage of each localized state, which is far from Fermi level. We found that at zero we have each localized state at Fermi, but this is the total one. As the hopping increase, actually it's decrease until it comes to zero, from 0.3 until 0.3 until 1.4. We have there is no actually Fermi localized density of state near Fermi level, which actually explain the experiment result. Here we don't have near from experimental condition, we don't have localized state at Fermi level, but we have more some localized state density of state away from Fermi level, which found experiment in STM experiment. As we increase the hopping, actually it begin after about 1.6. It begin again localized density of state, which do not exist in our experimental condition. The method, as we see here, this method gives us the realistic behavior of edge localized state of graphene. One, the result explaining the measured localized density of state at the edge of graphene, and at the same time removing the ecosystem between the semiconductor behavior found in the experiment data and for fabricated one and expected theoretical semi-metallic behavior. We study next neighbor for square, for honeycomb lattice, graphene, honeycombs, armchair with zigzag. But what if we have next nearest neighbor effect introduced to our model? We here introduce our calculation, the term of next nearest neighbor, and we calculated our dispersion relation. We will get some matrix encode the geometry here. This is our result here for zigzag case. We found, as we hear, the next neighbor hopping is 0.036 from the next neighbor hopping. So as we see that the Fermi level shifted, and the symmetry begin between the two, between the inertial dispersion become removed, here become more expanded, and here becomes squeezed, increasing the next nearest neighbor hopping. Actually, the effect of this one is very clear here. We here squeezing the number of modes and expanding the modes here. Also, Fermi level begin to move. We note here that Fermi level localized state of the at Fermi level become not flat as the normal case when we neglect next nearest neighbor interaction. As we increase n, it begin to make bending for the localized state. It's very clear in the odd case because here the bending in the Fermi level localized state is very clear. If we increase the nearest neighbor value to be very near from the nearest neighbor hopping, we found that the dispersion relation begin to completely change. Not only distortion for the dispersion later, but completely it changed for that. If we apply the method for square lattice, we have here the effect of 0.1, and here for we at the same in larger energy, we have expanding in the energy mode here, while decreasing we have a squeezing for the energy mode here. When we increasing nearest neighbor, the squeezing is much more higher, and here expanding is higher. Our result shows that introducing nearest neighbor interaction to the model removes the material dispersion relation symmetry around the Fermi level, and shifting the Fermi level while increasing the strength of NN interaction compared to NN can completely change the dispersion relation. For artificial magnetic properties, as we see, can fabricate and control NN interaction and the NN interaction, we can actually tune the properties of the material to be suitable for our desired properties. The result also shows that the two-dimensional material sensitivity for NN hopping effect is dependent on the lattice structure. If we compare between square lattice here, at the same value with hexagonal, we found that the effect in square lattice for nearest neighbor is less. It's the same value. It's very clear the distortion in the dispersion relation is higher in hexagonal or honeycomb lattice than the square. This is coming from the number of neighbor in nearest neighbor in the honeycomb lattice is 6, when next neighbor is about 3. So we have double probability for nearest neighbor. While in square lattice we have 4 for next neighbor and also 4 in for nearest neighbor. So the amplification is small. So this shows that the sensitivity of the effect depends on the number of nearest neighbor for the sides, which depend on the structure of the material. All these properties allow to us to fabricate many material that can use it in magnetic storage devices or electronic devices. So in many applications, we need more tunable properties. Not like this intrinsic is not easy to be tunable. In the graphene, they found that forming of 2 bilayer system of 2 graphene layer on top of each other, and then they can easily tune the properties by applying field or changing any layer. In this case, we here are both two Hamiltonian upper layer, top layer, bottom layer, and the interaction between the 2 layers. We found that E matrix is consisted of block diagonal matrix. Is what block is contain all the hopping in 1 layer, and then we have off block diagonal, which represents the inter-layer hopping. Here we show that we have a lot of parameters we can use to tune the properties of bilayer system. Here for the exact case only, we show that as we increase the interlayer hopping, the dispersion of the two bilayer system begin to distort here, and as we increase here, both the one asymmetry, both next to next neighbor in 1 layer, and see the effect, we have more distortion here. We see here that we open line point of contact here. As we have one impurity line in 1 layer, for example, top at 11, we introduce this near Fermi level extended state. And as we see, we have a lot of parameters easily can tune the properties of the 2 bilayer system. The obtained dispersion relation for zigzag and armchair bilayer system, nano-ribbon and magnetic square bilayer strip shows that the bilayer system easily gives the possibility of tuning their properties by changing many parameters, adjusting the interlayer hopping strength by changing the interlayer distance, adding different impurity configuration in individual layer, changing the range of interaction in individual layer, beside many other possibilities. Also, the result shows that the sensitivity of the bilayer system to any parameter is depend on their lattice structure. Conclusion for our study is that the obtained result is this issue that the physics of Heisenberg Hamiltonian system and die-binding Hamiltonian system for two-dimensional material are nearly equivalent and are reflection of their equivalent from geometrical point view and the topological point of view. Both systems represent exchange of hopping of particles. Here, in case of graphene, it's electron which fermion, and in case of magnetic case, is boson which magnon. Under short ring interaction with the nearest neighbor, so the same when we have the same lattice, we have the same range of interaction, and when we from electronic or magnetic, when we talk in second quantization language, we found that it's very similar. This led us to that we have a lot of research in graphene. So this may mean that we can, with a lot of we can apply many methodology applied to graphene and the graphene bilayer system. Can we transfer easily to other two-dimensional electronic material, magnetic material, and their bilayer system? The work can be extended. In this case, we can study the effect of strip width, edge axle anisotropy, and impurities, with including in hopping as well as forming of bilayer system of electronic and magnetic excitation in the two-dimensional material. Also, we can include in our calculation was for only square lattice and honeycomb lattice, but we have many possibilities for other two-dimensional crystal lattice structure, which can be studied as this model and can help to designing many new applications in electronic and magnetic. Okay, thank you.
Okay, thank you very much. There's some time for questions. Anyone have a question? Oh, well, I can ask.
Oh, yeah, okay.
So you showed many results.
Okay.
You find that tuning these parameters is important to fabricate the materials you want. Did you compare any of your calculations to